we have considered the example of a raised to I, b raised to j, c raised to k, where j is equal to I plus k. This was the last example which we have done. Yes, any query in this? And we have discussed the grammar, that here we have to replace this j with I and k, I plus k. So we are getting two different languages, L1 and L2, and here it is a concatenation of two languages, L1 and L2, where L1 language is a raised to I, b raised to I, and L2 language is b raised to k, c raised to k. So when you consider this, we have a grammar for L1 language. S1 gives A, S1B, or AB. We also discuss why it is AB, because I is greater than or equal to 1. Similarly, we have L2 language, where S2 gives us B S to C, because it is B raised to K, C raised to K, and B and C. So A is greater than or equal to 1. So we are considering BC as a terminating condition. And we are not using null for that. And to do a concatenation of these two languages, L1 and L2, we are writing L a language as gives S1 dot S2. So it is giving us the concatenation of the two languages. So this is what we have discussed. We have also derived the strings. So now let me change the condition slightly, and instead of I plus k equal to j, let me add a different condition in the same example, and let us write as I equal to j plus k. Let's consider it this way: I equal to j plus k, where j and k greater than or equal to 1. Let's modify the condition only. And we have the same language, a raised to I, b raised to j, and c raised to k. So let's consider in this way. We have a raised to I, b raised to j, and c raised to k, where I is equal to a plus k, as you can see here, and also j and k greater than or equal to 1. So if we modify this thing, can anyone suggest the grammar which we can write for this new language? Because if you put the value of I is equal to j plus k, you will get a situation like this: a raised to a, then we will get a raised to j, and we have b raised to j, and c raised to k. If you put I is equal to j plus k, because order of a is not significant, you can write a raised to k, a raised to j first, or you can have a raised to j, a raised to k. But this will give us some hint that how we can proceed further in this example. So from this, can we generate a grammar? Can you write in the chat window that what we'll get from this? Again, it is having a two different languages. If you observe the pattern, can you identify the two languages present in this language L? Yes, you can try out, no problem. If there is something wrong, it's not a big issue, because we are here to learn the things. If we learn, and we can learn easily from our mistakes. So which two languages are present in this? Can you tell? Yes, Sankit, if you want to say something, you can tell. Okay, here it is L1, which is A raised to K, then L2, C raised to K. Yes, we can say something like this. So, yes has given a grammar for that. L1 gives AS1B. No, here if you observe the pattern, you can see that occurrences of A and B, A raised to J, B raised to J, they are inside A raised to K, C raised to K. So if you do a concatenation of L1, L2, you will get a pattern like A, B, A, C, right? You can generate a string like this, A, B, A, C. If I do a concatenation of L1 with L2, you cannot change the order of A, B, C. All the A must be in the beginning, B must be in the middle position, and C must be at the last position. So this is what you cannot do. But definitely what Priyank has mentioned, A raised to K, L2, C raised to K. Right? So we need to generate A raised to J, B raised to J inside this A raised to K, C raised to K. So according to that, we should write a grammar. So can anyone write? So yes, I got some answer from Shweta. Okay, SASC. So we are repeatedly generating recursively ASC. Okay, now once it is over, you will replace S with A and C. That's good. The last iteration. And then from A, you are generating A, AB, AB. Okay, that's true. That is how we'll get the patterns. If I want to generate the pattern, which is definitely a correct answer, if I want to generate this AA, B, C, right? So it will be like this. From S, we'll get small a, capital A, C, because we want one occurrence of A and C. Now I will replace capital A with small a, capital A, B, and then C. But in that case, we will get more occurrences. So we have to directly use the terminating condition. So finally, we'll get A, B, C. This is how you can generate this answer A, B, C. So I think it is clear how we can write. And first, we have to terminate the outer thing, A, C. And once it is done, we have to replace the middle symbol with non-terminal A. So exactly similar, not same, but similar answer is here. Let us go through that. Right here, the condition is slightly different. You can see I have mentioned J and K greater than or equal to 0 instead of 1. So you can see a slight difference that I is equal to J plus K. So we are substituting the value of I, J plus K. So we are getting two groups as we have discussed, A raised to K, C raised to K. And inside that, we are getting another group, A raised to J, B raised to J. So you can see from S, we are getting ASC. And now we are replacing S with non-terminal A. And then for non-terminal A, we are writing A, small a, capital A, B, or null. So because J and K both are greater than or equal to 0, we are also able to generate null from this given grammar if it is required. So I hope it is similar to what you have written, because in that chat window we have considered the condition as J and K greater than or equal to 1. Here in this slide you can see J and K we have considered as greater than or equal to 0. So there is a slight difference, but I hope you can understand both the things. So there is no need to further discuss this. Okay, let's go for one more. This is how you can derive the pattern using the set. We have discussed this in the chat window, AABC. Then you can also derive like this, triple A, B, B, C. So from S, we are generating A and C, outermost thing. So A, capital S, C. Now we replace capital S with capital A. And for capital A, we are writing small a, capital A, B, and C. And again for capital A, we are writing small a, capital A, B. So we have triple A, B, C. Yeah, this is how we will get the derivation. We have third condition. K is equal to I plus J. It is similar to the previous one. So we are directly going to the solution. A raised to I, B raised to J, and C raised to I plus J. Now we are substituting the value of K, which is equal to I plus J. We are getting C raised to I and C raised to J. So if we reorder the C, we can write also like this: A raised to I, C raised to I, the outermost one, and inside that we have B raised to J, C raised to J. So again we have the similar situation. Outermost side will generate A and C. So recursively, so we have S gives A, S, C, or A. We are recursively generating A and C any number of times. Once it is done, we replace the non-terminal S with non-terminal A. And for non-terminal A, we are replacing it with small b, capital A, small c, BAC. And then we are putting null. And then we are putting null. So this is how we get the solution. So I hope it is straightforward. So let us move towards some more interesting example. So I am sharing another slide with you. Okay, here it is. These are more interesting examples. Let us have the different condition. A raised to I, B raised to J, C raised to K. But here the condition is J is greater than I plus K. J is greater than I plus K. So we'll write, because J is more than I plus K, we have to write J is equal to I plus M plus K. We write J is equal to I plus M plus K, where M is greater than 0. Where M is greater than 0. Because the occurrences of B are more than A and C. So definitely M cannot be 0 here. This is a very important step, that we cannot take the value of M as 0. Because if you take M as 0, then what will happen? That it will give us condition J is equal to I plus J. So here it is given that J is greater than I plus K. That means it is obvious that we cannot take J equal to M equal to 0. Yeah. So now what we have to write? It is giving us A raised to I, B raised to I, B raised to M, B raised to K, C raised to K. So we have three languages, concatenation of three different languages here. L1 language, A raised to I, B raised to I. L2 language, B raised to M. And L3 language, B raised to K, C raised to K. So now we have a concatenation of three languages. So we'll take first language L1 and we'll take the starting symbol as S1 of that language L1 and we'll write AS1B, AS1B or null. Here we are assuming that I and K can be greater than or equal to 0. Here we are assuming that I and K can be greater than or equal to 0. We are writing AS1B or null for the L1 language. Now similarly for the L3 language, let us discuss L3 first. So for L3 language, we'll write B S3C. We'll write B S3C or null, where B and C are equal, and we have null for that, because we are assuming that K can be greater than or equal to 0. Now we want to generate independently B raised to M. It is not depending on any another criteria. So we are generating b raised to m here. So to generate independently, we are writing S2 gives b S2 or b. So here we are writing S2 gives b S2 or b. So we are recursively generating only b, because as you can see, we can generate any number of times b from this. If we write like this S2, we are getting a b S2. Then again we'll replace with b S2, so we get b, then b S2, and at last we get this. You can see that recursively we are generating any number of times b. And here we are terminating with b. We are terminating this recursion. S2 gives b S2 or b, because m must be greater than 0 to satisfy the criteria. So that's why we are writing S2 gives b S2 or b. Here question can we write S2 gives S2b? Can I write like this? S2 gives S2b or b? Is it valid? Yes, here we can write, because we want to generate independently b. We want to generate independently b. So if you write in this way, particularly in this case, because b raised to m is independent and it is not changing the order. So we can also write like this: S2 gives S2b or b. Then there is no issue, particularly in this case. And at last, we have to do the concatenation of three languages, L1, L2, L3. And to achieve the concatenation, we are adding the rule S gives S1, S2, S3. That's why we are adding this extra rule. S gives S1, S2, S3. The concatenation of three different languages. Now using these three languages, we can derive the string. So we are deriving the string A, B, B, C. You can see that AB will be derived from the non-terminal S1, BB which is derived from the non-terminal S2, B, and last BC, the last group BC, that will be derived from the non-terminal S3. So can we say that we are partitioning the string X, which we want to derive, into three strings, X1, X2, X3 substrings in a general case, where X1 is derived from S1, X2 is derived from S2, and string X3 is derived from the S3 in a general case. So what is the first step we have to take always? That from S, we have to write S1 into S2 into S3. That is the first step. Always we have to apply that. And that is required for the concatenation purpose. And now from S1, we'll derive A S1B, then S2 and S3 as it is. Now from A S1B, we are getting AB, because we are replacing S1 with null. We are replacing S1 with null. We are getting AB, S2, S3. We are getting AB, S2, S3. Now from S2, we want a 1B. So directly we'll use the terminating condition. We'll replace S2 with B. And at last, we have S3. So for S3, we'll get S3 as it is. And then we'll derive B S3C from it. And as you can see here, that last put S3 equal to null. We are getting AA, B, and BC. That is the required string. So, do you have any query in this? So basically what we have done, we have just understood this theory part using this example. What we have done is we understood the theory part, that if we have any context-free grammar, V sigma SMP, which is generating the language L1, L2. So we are deriving the required string X from that new grammar. And for concatenation purpose, we need additional rule, S S1 into S2, as we have done. You can see that we have two languages, L1 and L2. So we can have a concatenation of L1, L2 possible. So to achieve the concatenation, we have to add the extra rule into the set of existing rules. That's why you can see it is mentioned PU. The set of rules for the union operation is equal to rules of P1, that is the L1 language, union rules of the L2 language, which we are denoting as P2, production rules of the L2 language. Along with that, we require one additional rule, S gives S1 into S2 to achieve the goal. And to derive any string X, we have to take as X1 into X2, we have to partition it. And we are able to derive the X1 string from the L1 language, and X2 string will derive from L2 language. So what is the first step? The first step for the concatenation operation, here they are using the symbol SC. C is the suffix. So SC indicates it is the starting symbol for the concatenation language or the final language, which is giving the first step as S1 into S2, concatenation of S1 and S2. And then from the S1 using several steps, you can see a star using 0 or more steps. Using 0 or more steps, you are able to derive the X1, and then from that S2 using 0 or more steps, you are able to derive X2 part. This is how we are able to derive the string. That is what we have to understand from this slide, that when you consider any two context-free languages, their concatenation is a context-free language. We require additional rule for the concatenation, and some portion of the string will be derived from the first language, and the remaining portion of the string will be derived from the second language, that is the L2. And similarly, you can extend this for three languages, as we have seen in the previous slide. We have three languages, L1, L3. So it is very easy to understand what this theorem tells. So let us proceed further. Okay, let us have a new kind of language, A raised to I, B raised to J, C raised to K. We have I is equal to J or J equal to K. So we have OR condition here. Either I and J are equal, or J and K can be equal. So you can see that we are only comparing two entities, I and J, or we are comparing J and K. We are not comparing all three, I, J, K. So we have one language L1, A raised to I, B raised to J, C raised to K, I equal to J, and K can be anything. Because when you consider I equal to K, there is no rule for the K. So K can be 0 or K can be greater than 0 also. So if we rewrite this, we are getting A raised to I, B raised to I, because I is equal to J, and C raised to K. So from L1 language itself, we are getting two languages. From L1, we are also getting two languages. So I'm giving them L11 and L12. And it is a concatenation of two languages, L11 into L12. Right now, we are just discussing about the L1 language, right? We are discussing about the L1 language. Then we'll discuss also L2 language. So as you can see, for L11, it is raised to I, B raised to I. So we are writing AS11B or null, because I equal to J. So both A and B can be null also. So only C raised to K may be possible, because when I equal to J, K can be anything. So we are writing S11, which is AS11B or null for the L11 language, and for L12, because it is the second part of the L1 language. So we are giving the name L12. So for that, we take a starting symbol as S12, and for this S12, we are getting, because we are generating independently C raised to K. It has no dependency on A or B. So we are writing CS12 or null. That's why we are writing CS12 or null. And last, we have to do the concatenation of these two languages, L11 and L12. So we are writing S1 is equal to S11 into S12. So for this, we are writing S1 is equal to S11 into S12. It is a concatenation of two languages, L11 with L12. This is what we are writing for the L1 language. Similarly, we want to write for the L2 language. So for the L2 language, can anyone write what we will write in the grammar? Because our actual language L is a concatenation of two different languages. Our actual language L is a concatenation of two different languages. So can anyone write about L2 language? So yes, one student is in the L2 language, A raised to I, B raised to J, C raised to K, J equal to K, and I is greater than or equal to 0. So what we require is, we should have J is equal to K. So B and C must be equal. So we are writing L21, which is equal to A L21. We are independently generate A because there is no rule for A. We can generate independently, and then we have L22, which is giving us B L22C or null. B and C are equal, and it is a concatenation of two languages again, L21 with L22. So we are writing L21, L22. So only thing which I suggest is you should write a starting symbol as S, not L, because S is the normal convention for this thing. Instead of L, you should use S in all these places. Definitely L is not incorrect, but it is better that you use S. Normally L we are writing for the language, and S is indicating the starting symbol of the grammar. So prefer S over L, right? Definitely it is a concatenation of two languages, L21 with L22, and we are getting the L2 language, right? So let us see what Priyank has written. Almost same you will find. So at last what do we get? You will get the concatenation of the two, right? At last we have to do the concatenation of two here, S21 with S22. It is similar to what Priyank has written. And we are able to derive the string as well, AABC, where you can see A is independent and B and C are equal. So from S, we are writing S2. Now, this step is very important. S is equal to S2 because our actual language is what? Language L, which is either I equal to J or J equal to K. Our actual language L is either I equal to J or J equal to K. So to achieve this OR operation, we have to add one extra rule, S, which gives us S1 or S2. I hope you're getting this step. It is the union of two context-free languages. We need extra rule. S gives S1 or S2. This will tell us that either you have to go for S1 or you have to go for S2. You cannot jump from S1 to S2. Once you start the derivation with S1, you can not select the other path S2. These are two different paths, S2 S1 or S2 S2. So as you can see here, that to derive this particular pattern, AABC, AABC, we have to select B and C equal. We are selecting the path S gives S2. We are selecting the path S gives S2 because it is considering J equal to K. So we write S21 into S22, a concatenation of two languages. Now from S21, we write small a S21 having a concatenation with S22. Now to derive the AA string, we are writing AAS21 and we'll write S22. Now from S1 we'll replace with null. So we are getting AAS22 and from this S22 we'll write BS22 and C. We are getting BS22C. So finally we'll get AABC. Finally we'll get AABC. So I hope you are getting this. So we are getting this thing. So we can also write this concept in the form of theorem like this. The same as our previous, only difference is we are discussing this theory for the union operation. If L1 and L2 are context-free languages, then L1 union L2, then L1 union L2 is a context-free language. So what it tells that here we have to add one extra rule into the production. So PU is indicating a union operation, which is equal to all the rules of the first language, P1 union, all the rules of the second language, P2 union. We need one extra rule for the union operation, I equal to J or I equal to K. So that union operation, we need this rule. SU gives S1 or S2. SU gives S1 or S2. And now also the set of non-terminals. In the set of non-terminals, we are adding one extra non-terminal. As you can see, V1, the set of non-terminals of the first language. Then V2, set of non-terminals of the second language. And along with that, we need one extra non-terminal SU. And this is always required, as you can see, this is always required. Right? It is also required in concatenation as well. One extra non-terminal for the new rule. So when we are doing a derivation, here the only difference is we have to select any one path. If we want to derive X, which belongs to L1 language, then we have to use the rule SU gives S1. If you want to derive X, which belongs to L1 language, then we'll select the rule SU gives S1 as a first rule, and then we'll use all the rules of the P1 set. Similarly, if your string X belongs to L2 language, then you have to select the first rule as X gives S2, and then we have to follow the rules of the second language from the set P2. So that is how you can derive the string X, which is in either L1 or L2. So a string which is in either L1 or L2, same string is also in the language L, because we have to just use one additional step. S gives S1 or S2. We have to perform one more step to show that X also belongs to the L language, which is a union of L1 union L2. one extra step is required to show that x belongs to L. I hope things are clear. So the discussion is here in this slide, as you can see. And we also seen this theorem with an example in the previous slide. Okay, so let us consider this I equal to j or I equal to k. So let's consider this. So can anyone explain what is the role of different symbols here? Yeah, we can use any non-terminals, as I said. So can you tell me what this S gives V indicates in this? Here it is a different example, I equal to j or I equal to k. Or if you want to solve in our own way, we can also solve like S11, S12, which is more preferable over this. Right? So we'll solve our own way also, a raised to I and b raised to I and j are equal, and c raised to k. If we solve like this, a raised to I, b raised to I, and c raised to k, because I equal to j. So can you tell what is the role of S gives tu here? What is the purpose of this S gives tu? So can I say this T is equal to S11 and U is acting as S12, because this is your L1 language. I equal to J. I equal to J is your L1 language. So here you can see the role of T is same as S11 and role of U is same as S12. If you solve our own way. Is this clear? Right? We are doing a concatenation of S11 with S12. Because A raised to I, B raised to I is your L11 language. So it starts with a symbol S11. And C raised to K is independent. So it will start with S12. S12. So that is how we have T and U here. So can you tell what is the role of V and W? Or you can derive in your own way. Just consider V and W. So it is like this, A raised to I. We can derive our own method also. B raised to A and C raised to I. Right? We can write like this. A raised to I, B raised to J, C raised to I, which is another language. So can anyone explain what we are doing here? Because when I is equal to K, we are getting this A raised to I, B raised to J, C raised to I. When I and C are equal, and we are generating independently B. So can you tell what will be S21 here and S22? Can you write this in the form of S21 and S22? Or S21, or you can also take S2 if required. You can use any symbol. You can write in the form of S21 and S22 also. You can write in the form of S2 and also you can generate the grammar. So can you match the terminals? Let us match this. What will be S21 here? And what will be S22? S22 here. In this grammar. Yeah, if you can say. And know that you can give the answer. There is no issue. You understood the thing. Whatever you have written in that window, it is straightforward now. That you are getting the things. Yes. Yes. Do you have any query? Which non-terminal is indicating S21 here? And which non-terminal is indicating S22 here? Yes. Yes, if you have any query, you can ask. Okay, I got one answer. S2 is equal to V. Okay. You are taking S2, which is equal to V. Okay. So we can write like this. S2 gives A S2C, or now we want also W. Okay, what Priyanka has written, S21 is equal to A S21 B or null. So we have A and B. Okay, so this is you are writing for the L1 language. A and B are equal, I equal to J, right? No, I think something different you are willing to tell. No, when I is equal to K, that means I, A and C are equal. B is independent. Yeah, I think you need to check this. Right? I think you have written, you want to write C there in S21. In S21, you want to write C there because that is the only small mistake in that. In hurry, you have written B. By mistake, you have written B there. Actually, it should be S21 gives A S21C or null, right? Because A and C are equal. And then for S22, you are writing B S22C because B is independent. Okay, now only small problem is how we move from S21 to S22. You need one extra rule. You cannot write null. Need one rule. A S21 because you are generating this E inside ANC. Are you getting it? Yes. S21, which will give us A S21C. You are generating A and C first, and then inside it you have to generate no. Now in this case, what will happen? This rule will not become recursive rule. You cannot generate recursively A and C because you have two different non-terminals. S21 gives A S22C, so it will create a problem, right? You cannot apply this rule several times. You can apply only once. So what Yash has written, that is the correct thing. S21 gives AS21C or S22. And for non-terminals, we are always using capital letters. Right? Keep in your mind always that for non-terminals, that is a common rule. We have to use always capital letters with suffix if required. For terminals, there is always small case letters. So what yes is written, S21 gives A, S21C or S22. And now once you recursively apply that step, and you have to replace S21 with S22. And from S22, you can generate B inside NC. So I hope this is clear. So here the role of W is like S22 and role of V is like S21. Right? W is like S22 and S21 is same as non-terminal V. Yes, so for S2 also you can write S21. Right? Instead of S21 you can write S2. Both are same. You can use any variable in this case. Role of S2 is same as S21. It is correct. Okay, so let us proceed further. You can see that these examples are normally having a weightage of 4 to 6 marks. If you write this down correctly and you derive the string, you will score 4 to 6 marks depending on the complexity. This is also here discussed several times that if we have independent language like V raised to M, as we have seen previously, right? We have seen several times. Here we have seen that C raised to K, it is independent. We are getting C raised to K when I is equal to J. When I is equal to J, we have C raised to K, which is independent. When I is equal to K, we have B raised to J, which is independent. Basically, it is telling that if L is a context-free language, we can generate L star because B raised to M is nothing but L star. So we are adding the extra S gives S S1 or null. We are getting a rule S gives S S1 or null. Just we have to add one extra rule, and what we are doing. Right? Here we are writing like this. U gives C U or null. So it is same as that. You can just map this theory with this line. U gives small c capital U or null. Or you can map with W gives small b capital W or null. W gives small b capital W or null. So that is how you will get U and W. So these U and W rules are indicating that we need extra rule like this. S gives S S1 or null. Right? The S we have recursion and we have null for that. So S gives SS1 or null. You can see that either you can write SS1 or in some cases you can write S1S. Both are correct. Right? S1S also is valid rule. S gives S1S or null. So here writing in this way. S gives S1S or null in previous example. So along with other rules, we need an extra rule to generate the L star. Here we are considering that your language L is your only B. For a U, non-terminal U indicates your language is only B. So we can say that this is your U star. Right? When you are writing this, it is your U star. So let us see one more interesting thing, that for every regular expression, we can write a context-free grammar, because we know that CFG is more powerful as compared to regular expressions or regular grammar, because we can do the comparisons while it is not possible in the regular language. We cannot do a comparison. because we don't have any kind of memory. In case of context-free grammar, we are using a push-down automata, and for that we have memory as a stack. So for every regular expression, we can write its equivalent context-free grammar. So now what A plus B represents? It is indicating A or B. So to consider A or B, we write like this: capital A, which gives us small a or B. So we are writing A plus B. We are writing A plus B. Now we want to write A plus B star, because we have only 3 operations in the regular language. That was also your question in internal. Find the regular expression in regular language. It will tell that regular language is obtained through 3 operations, 3 primitive operations: union, concatenation, and closure. So here you can see that you are doing a union A or B, and we are writing A gives A or B, either A or B. Then for A plus B whole star, we are writing B gives B A or null. We are writing B gives B A or null because it is your star. So we are using the same concept as the previous theory. If L is any language, then we can get L star. We are using this extra rule. S gives SS1 or null. We are writing S gives SS1 or null. So here we are writing B gives BA or null. Right? Because L star, we are considering L star, where L is your A plus B. So L star is B gives BA or null. This is how we are getting the L star. And then to do a concatenation, we are writing S gives capital B for A plus B star, and that we are doing a concatenation with AB. You can also take other non-terminals if you want, but this is sufficient. That S gives capital B AB. So last we are getting AB. So it is a concatenation of 2, we can say 3 different context-free languages. The one language is capital B, second language is small a, and third language is small b. So S gives capital B, small a, small b. So it is a concatenation of 3 different context-free languages. So I hope you are getting this, how you can convert regular expressions to CFG. So let us see one more example for practice. So you can see it is BBA, AB star. You can see it is BBA or AB star, one regular language plus union. We have another regular language, AB plus B A star B whole star and BA. So let's consider the L1. So you can see that what we are writing for AB star, right? You want in the beginning BBA. You want in the beginning BBA. So you are writing S1 gives S1 AB. We are considering S1 gives S1 AB. So you can see that at last, when you replace S1 with BBA, you will get the pattern BBA AB star. Let us see that how we are getting this. S1 gives S1 AB. Then further, I want AB star. So I will write S1 gives S1 AB. As you can see here, so I am getting AB star. I am repeating AB any number of times. I am repeating AB any number of times. Further, if you require, we can write like this. S1 gives H1 AB, AB, AB. And at last we'll replace with BBA. I hope you can see this derivation and you will understand that how we have written L1. Right? BBA, AB star. BBA, AB star. Similar approach you can see for the L2. Now here it is different. AB plus BA star whole star. AB plus BA star B whole star, and we have BA. We are writing S2 gives TS2. We are writing S2 gives TS2, where T is repeated. You can see for S2 we'll write TS2. Again for S2 we'll write TS2. Again for that we can write right. So you can see that we are repeating the AB plus BA star B whole star. We are repeating AB plus BA star B whole star to this non-terminal T. Okay, now in non-terminal T, you can see we have two options. Either we want to repeat A, or you want to repeat B A star B. Either you want to repeat AB or you want to repeat B A star B. So for that T, we are writing AB or BUB. BUB. Right? We are repeating B. B A star B. So it is BUB. So for first T, let us write AB. For the second write, we write BU. For third T, let us write again AB, and then we have H2. Now for U, I can write AU. So I will write AB, then B, AU, B. So BUB, I'm replacing U with AU. Then again AB, H2. It will further give me BBA. I'm replacing U with null. B, AB, H2. And finally for H2 we get BA. So we have AB, BAB, AB, BA. I hope this grammar and derivation is clear now. Yes, do you have any query in this? Today, I can say that 3-4 students are actively participating. Priyank, Yash, Ronak, Shweta, Ujit. Right? The students have participated very well in class discussion, because if you participate, you will understand the things more better. If you have any query, we can solve during the lecture itself. So I hope this is sufficient for today. We'll see more interesting things in the next lecture. Thank you.